Alright guys, good evening everyone. This if you're online, indicates your presence when you're online. Good evening guys. Good evening guys. If you're active, indicate that you're active. If you're online, indicate that you are online. If you're online, indicate that you're online. So we can start proper. Please, if you're active, indicate that you're active. Please, if you're active, indicate that you're active. We're about to start. Please indicate. Indicate. Indicate that you're active. Please indicate that you're active. Indicate that you're active if you're online. And please, if you have joined the live class, quickly share the link to your classmates, share the link to your school, share the link to your departmental WhatsApp group. Just share the link on social media. Let's connect other students across the globe to join us so we can start. All right. Please just share the link. Make sure you like the video. Share the link. Please let's share and connect others. Please indicate in the comment section if you are active. Indicate. We are starting tonight on continuation of where we stopped in our previous class in electrostatics. So we shall be looking at this topic. But the aim of today's class is for us to have proper understanding on how to solve some practical problems regarding Coulomb's law, okay, and how to find the direction of a particular force over a given charge, over a given point charge, right? Then we'll also be looking at the principle of superposition of forces, meaning if we have more than two charges in a system, then how do we find the action of a force over other forces in the system? These are the things we'll be discussing tonight. Okay, it's a continuation of where we stopped. For those of you who are not in the previous class, I will quickly advise that you go through the previous live class we had on electrostatics, because after tonight, our next class will be on electric field intensity. Then we're also going to electric potential and work done in an electric field. Then we are done with this topic. All right. Then after then we'll move into Gauss's law. All right, and its application. So please, we have a lot to cover in this season. Okay, in physics, we can be having continuous class in physics. I will advise every student to be active throughout this class. All right. So please, if you have shared the link, indicate in the comment section that you have shared the link. Indicate. All right. So in our previous class, we discussed about electrostatics, right? And we define the concept electrostatics as a branch of physics that deals with the study of charge at rest. We say the word electro is from the word electricity. This is a review. Electrostatics. The word electro is from the word electricity or electric charge, right? Electric charge. While statics means the word rest. Statics means the word rest, meaning this is the study of charge at rest. It's the study of charge at rest. I also say that we have um, two types of electricity or electric charge. We have what we call static electricity, which is what we call the electrostatic. Then we have what we call the current electricity. The current electricity. Current electricity or current charge, right? Current electricity. Okay, we have the static charge. Also, we have the current charge or the current electric charge or electricity. This talks about the flow of electric charge through a conductor from one terminal to another in an electric wire, right? Is a flow. But when you hear the word static, static means the study of charge at first. Then in a previous class, we talked about what is an electric charge. We define electric charge as one of the fundamental properties of what? Of matter, right? Then we say we have types of electric charge. We have the positive charge, the negative charge, and the neutral. And we said in our previous class that the negative charge, these are charge that are electron rich. These are charge that are electron rich. They are called the negative charge. A good example of such kind of charge is called the electrons, right? Now we also have what we call the positive charge. So these are charge that are deficits. They are electron deficits, meaning they lack electrons in them. A good example of positive charge is called proton. Then we have the third one, which is called the neutral charge. These are charge that have equal number of positive and negative charge. A good example, we have the neutron, right? Then we also talked about the properties of electric charge. We talked about the first one, which is the fundamental properties that says that like charge repels, unlike charge attracts. Number two, we say that charges are quantized, meaning charges are quantized. They are in discrete packet, they are in a fixed amount. And instead, the quantized charge is given as Q equals to what? NE, where N represents what? Whole number, whole number, where N can either be what? 1, 2, 3, right? Then we say that one electron is equivalent to 1.6 times 10 to the power of minus 19 Coulomb. This is what the second properties of what of electric charge. Number two, we say charge are quantized. Number three, we say that charge can not be created or destroyed, but can be transferred from one point to another. We can transfer charge. We can transfer charge. The fourth one, we say that the total charge of a system is the sum of the algebraic individual charges in that system. The total charge of the system is the sum or is the algebraic sum of individual charges in the system. And we say that the total charge, Q total, is equals to Q1 plus Q2 plus Q3 down to Q what? N. Right? Then the next thing we talked about in a previous class is Coulomb's law. We stated Coulomb's law and we came to conclusion that from Coulomb's law, that the force of attraction is equals to K Q1 Q2 over what? R squared. The force of attraction, the electrostatic force, okay, between 2-point charges, between 2-point charges, between 2-point charges Q1 and Q2, separated by a distance R in meter. The force is given as KQ1 Q2 over r square times direction of action of that force. Okay, this quantity here represents the size of the force, right? While this represents the unit vector, which indicates the direction of action of a particular force on a charge over the other charge. All right. Then I explain what this direction of action means. That if we have 2-point charge, all right, there's always an action of a particular charge over the other one. There's always an action of force, okay, of a particular charge over what the other, right? Now, to find the direction of that force between 2-point charge, we have to indicate this. This means our unit vector. In our previous class, I gave how to find the unit vector or the direction of action, direction of action of a point charge over other charge, of a point charge over another what charge, another charge, right? Because we said that Coulomb's force is a vector force, and every vector must have a size and a direction. All right. We are used to finding the size of a force. All throughout our secondary school, we are taught how to find just the size. That if we have two charges, we have charge 1, charge 2, the value of K, we know that K is equal to 1 over 4 pi permittivity of free space, which is 9.0 times 10 to the power of 9, right? Newton meter square per what? Coulomb square. We all know how to find the value of this. The value of this, if we have Q1, Q2 separated by a certain distance, we can be asked to find the force. After getting the force, that value you got is called the size or the magnitude of the Coulomb force. But Coulomb force is not just a force, it's a force called a vector force, right? It's a vector quantity rather that have a size and a direction. So this represents the size of the Coulomb force. This represents the direction of the Coulomb force, which I called the direction of what? Of action. Are you getting it now? So throughout this class tonight, we'll solve like one or two examples, and this class is over. So throughout this class, we shall be analyzing Coulomb force and how to find the direction of the force over another force. And I hope you are following, right? I hope you are following. So let's look at one good example. If we are given a system of charges like this, we are given a system of charges. Let's check this material we have here. We have a system of charges. We have a first charge here, which is plus 14 microcoulomb. We have another charge here, which is minus 26 microcoulomb. And we have a third charge, which is plus 21 microcoulomb. And we are told that distance from the first charge, this second charge, this is the third charge. Distance from the first to the second charge is about 0.12 meter. Then distance from here to here is about 1.6 meter. And we are told that 3-point charges lie on a straight line, horizontal line as shown. Find the resultant force exerted on. Find the resultant force. Find the resultant force exerted on minus 26 microcoulomb and plus 21 microcoulomb. Okay, we have two questions. The first one says find the resultant force exerted on this. This is the first one. And number two, also find the resultant force exerted on what? 21 microcoulomb charge. Now listen. Yesterday we talked about the direction of action, that using vectors to represent direction, we must have to take note that in the Cartesian diagram we call this component what? S component, right? We call this what? Y component. In vector, the S component represents the I component. So this part is called the positive I. This part is called the negative I. This part called the Y is called the positive J. This is called the negative what? J. Now, for this question, we are dealing with I component because these vectors, so these charges are along what? The horizontal components. It's just like saying we have the first charge here, plus 14, right? The second one is somewhere here, right? The third one is somewhere here. So the three charges are lying along the I component, along the S component, also called the I component, right? Vector X represent I, vector Y represent what? J. Exactly? Okay. Now, what we do is that since we are asked to find the resultant force exerted on this, on minus 26 microcoulomb charge, that means that the direction of action is towards minus 26 microcoulomb charge. I explained all of this. Yesterday, we had a full class, over up to 2 hours class, explaining direction of action of forces. Please go back to that class and learn. For those of you who did not join us yesterday live, go back to that class and learn. But I will try as much as possible to explain this in detail for you to have a proper understanding. Now listen, solution to this. We have three charges here. I'm repeating my question. I have charge 1. I have charge 1 here. I have charge 2. And I have what here? Charge 3. Charge 1 is giving us 14 microcoulomb. Charge 2 is giving us minus 26 microcoulomb. I hope you guys are following. Okay, so let's proceed. Charge 3 is giving us 21 microcoulomb. And we are asked to find the force exerted on this, meaning the force exerted on charge 2. Charge 2, this is my charge 1, Q1. This is my charge 2, Q2. This is my charge 3. This is my charge 1. This is our charge 2. This is our what? Charge 3. To find the force exerted on charge 2, since we have more than 2 charges in this system, I'm going to use the principle of superposition of forces. Okay? From the principle of superposition of forces, the force exerted on charge 2 will definitely be F2, 1 plus F2, 3. I'm going to explain. For those of you who did not join the live class yesterday, to find the force exerted on this, it means that the direction of action, the direction of the force is on charge 2. We have to find the resultant force exerted on this. It means our focus is on charge 2. The action is towards charge 2. So we are looking at the direction of action from charge 1. It means that direction of action from charge 1 to charge 2, and from charge 3 to what? To charge 2. Find the resultant force exerted on minus 26 microcoulomb. So it means the force is moving from 1 to 2, 3 to 2. And that means our direction of action is towards charge 2. And now we say that our F2, which is the force exerted on charge 2, equals to F21 plus F23. F21 means direction of action is from charge 1 to 2, which is what I just indicated here, for 1 to 2. F23 means from 3 to 2, which is from 3 to 2. Let's look at this. What if the equation says, let's look at this second one. Find the resultant force exerted on plus 21 microcoulomb charge. This charge is the third charge, right? It means that find the force exerted on the third charge, which is called F3. So F3 will definitely be what? F3, 1 plus what? F3, 2. What does that mean? That the direction of action, they are all towards what? Charge 3. Meaning from charge 1 to charge 3 and charge 2 to what? To charge 3. It means that the pulling force is towards charge 3. For F2, the pulling force is towards charge 2, meaning the pulling force is moving from 1 to 2, from 3 to 2. For this, the pulling force is from, since they said on 21, we're not considering the fact that the pulling force is on charge 3, meaning from 1 to 3, from 2 to 3. What if they said find the direction of force on 14 microcoulomb charge, meaning find F1. F1 will then be what? Will then be F12 plus what? F13. It means that the pulling force is now towards charge 1, and that will now give us from 2 to 1 plus from 3 to 1. From 2 to 1 means F12. From 3 to 1 means F13. I hope that is becoming clearer. So let's go now. Let's find this. The first thing we need to do is to find F21. Our F21 is simply, the charge is simply charge between charge 1 and charge 2. F21 means from 1 to 2. It means I will consider just charge 1 and charge 2. To find F23, it means I'll consider just charge 2 and charge 3. Now let's go. From our formula, recall that force is equals to what? Q1, Q2 over what? R squared, right? Dot unit vector. So for this, to find F21, F2, 1 becomes what? Q1 is between charge 1 and charge 2. So we have charge 1 times charge 2 over what? R squared 2, 1 times unit vector of 2, 1. Now let's analyze this. This then will give us our K is, okay, let me fix the value here. Our K is 9 times 10 to the power of 9 times our Q1 is 14. We have 14 times 10 to the power of minus 6 times our Q2 is minus 26. Minus 26 times 10 to the power of minus 6. All divided by the distance between F2 means distance between charge 2 and charge 1. We are told is what? 0.12. Distance is 0.12 meter. Y here is what? 0.16. So that means the distance between this charge 2 and charge 1 will now be what? 0.12. All what? All squared. From the Coulomb's law. R squared, right? Times. Now the next thing is to find the direction of action. What we just evaluated is just this, right? The next is to find the direction of action, which is where is the action acting towards? It is acting towards from charge 1 to charge 2. Look at it here. Find the force exerted on this, meaning the action is from 1 to 2. For this, for our F21, it means from 1 to 2. And from 1 to 2, the unit vector there, this unit vector will be what? Positive I. Why is it positive I? Because in the Cartesian diagram, it is acting towards the positive x-axis. Look at this now. For this other one here, F23, meaning the action of force or the direction of action is from 3 to 2. From 3 to 2 simply means towards the negative or I. Negative I. Is that clear? So for this, our unit vector is what? Minus I. But for this, from 1 to 2, it means the action is this way. It's going towards positive I. So I will say times what here? Times I. Now let's finish up this. Let's multiply what we have here and see what we are going to generate. By the time we multiply 9 times 14, 9 times 14 times minus 26, okay? This will give us about F2, 1 becomes, let's go, 3276 times 10 to the power of minus 6. 9 minus 6 is simply minus 3, right? So 9 minus 6 is simply 3. Then 3 minus 6 will give us what here? Minus 3. All divided by 0.12 squared will give us 0.014. 0.0144. Is that clear? Now the next thing is to then times I, right? And that will give us finally, let's find the final expression here. This is minus 3, right? I can move my point from here 3 times to cancel out this minus. By the time I move my point 3 times, that will give us 1, 2, 3. This will give us about 3.2. This will give us about F2, 1 will give us 3.2 divided by 3.2i divided by 0.0144. Okay, so 3.2 divided by the answer, what we're going to be having here to be about 222.22i Newton. Okay, so that is the first expression for F21. This is the first answer for F21. All right. This is the first expression. 9 multiply with 14 times 26. Okay. Divided by, let me confirm again, 0.12 all squared. Okay, correct. Minus 3, 1, 2, 3. Sorry, I think there is a mistake somewhere. Let me verify 3.2 divided by 0.0144. Okay. 9 times 14 times 26. Yeah, it's meant to be. Okay, let's finish up this. Three two seven six divided by 0.12 all squared. Okay, there's a mistake. I've corrected that here. This will give us about, this is about 227,500 times 10 to the power of -3. Here we have here to be minus then I, right? Then F21 becomes, by the time we move our standard form now, 1, 2, 3. This will give us about minus 2, 2, 1, 2, 3, 227.5 I Newton. Okay, that is the correction. All right. Now, that is just that. So we have seen that F1 to F21 means for 1 to 2, for 1 to 2, meaning towards the positive what? I, right? Okay. Now the next is to find, let's find our F23. F23 will then be between chart 2 and chart 3. That will give us KQ2 times Q3 divided by, okay, unit vector, sorry, R squared from 3 to 2 times unit vector 2, 3. Okay, let's finish up this. So that means our F23 will be, let's go, our K is about 9 times 10 to the power of 9 times Q2 is minus 26 times 10 to the power of -6 times Q3 is 21 times 10 to the power of -6, all divided by distance between chart 2 and chart 3 is 0.16 all what? All squared. 16 all squared. Please, if you are following, indicate that you are following. Please, if you are following, indicate that you are following. Please indicate that you are following. Okay, let's look at this now. We have seen that F21 is between chart 2 and chart 3. Chart 2 and chart 3. So that will give us our K times Q2, Q3. Our Q2 is -26 microcoulomb. Then our Q3 is 21, right? All right, microcoulomb. Distance between chart 2 and chart 3 is 0.16 all squared. Now let's evaluate further. Okay, we're almost getting to the final answer. So 9 times -26. Okay, the next is to define the unit vector. Unit vector here simply means from chart 3 to chart 2. Look at it here. From chart 3 to chart 2, the direction of action is -I, right? Because we are going towards -I. In this Cartesian diagram, we are moving towards this region, -I. For this is what? Plus what? I, right? Plus I means towards positive I. This means towards negative I. So let's fix our value. Then we have times -I. So from here, minus times minus will give us plus. So let's go. It means the minus sign will cancel out. It will cancel out itself. So we have here 9 times 26 times 21. Okay. So we have F23. We then give us 4914 times 10 to the power of -3I, all divided by 0.16 squared. That will give us about 0.0256. So the next is to divide this with this. By the time we move our points 3 times, 1, 2, 3, we have 4.914, right? Let's do that. 4.914 divided by 0.0256. The final answer here becomes F23 equals to 191.1953 Newton. Okay, we have been able to get the direction of action from 3 to 2, which is 191.1953. The next is to find the force exerted on this charge, right? The force exerted on this charge. I hope I can clean this region now. So let's find the force exerted on that. The force exerted, therefore, the force exerted on minus 26 microcoulomb charge becomes F2 equals to, we are told that it's F21 plus F23. Our F21 is simply this, right? It's simply minus 20, minus 227.5I plus our F23 is 191.53I. Is that clear? So by the time we add up the force, our F2 becomes minus 227.5 plus 191.53. This will give us about minus 35.797 Newton. Okay, but this is not the final answer. The final answer here is now, listen, to find the force now, I have to take the absolute value, right? The absolute value of this is our F2 absolute. The force here becomes 35.97. Then the direction becomes towards the negative x axis, to a negative x axis. Let me explain this. Listen, the addition of these two forces, right, gave us this minus 35.97 I Newton. Now, this is the answer in vector form. But what do we do to get the resultant force? Is to take the absolute value or the modulus of this force. The modulus of this force in vector is simply 35.97, meaning I will remove this minus I. If I'm to remove minus I, what's the remaining here is what? 35.97 Newton, right? Then when you remove this 35.97 Newton, what remains there is minus I. The minus I indicates the direction. Minus I means negative x direction because I represent the x direction. So the direction of action, or the resultant force rather, is towards the negative x axis. But the resultant is simply what? 35.97 Newton. Okay, we are done with this first question. Then the next one says, find the force exerted on 21 microcoulomb charge. Please indicate that you are following. Okay. Now let's find the resultant force exerted on 21 microcoulomb charge, right? Exerted on the third charge. Now we now know better how to find this. To find the external force exerted on this, it means we are looking for F3, right? And F3 is equals to F31 plus F32. This is called the principle of superposition of forces, right? Okay, now let's find our F31. F31 is simply the force between charge 3 and charge 1. It means from charge 1 to charge 3. This is our charge 1, charge 2, and charge 3. So we're looking for our F31, okay? Force exerted on charge 3 means the action of force, the direction of action, they are all towards what? Charge 3. Meaning from charge 2, from charge 1 to charge 3, also from charge 2 to what? To charge 3. Are you there? From charge 1 to charge 3 is positive I. From charge 2 to charge 3 is also a positive I. Because both of them are directed towards positive x-axis in the Cartesian plane. Is that clear? They are directed towards positive I, towards this region. Is that clear? Okay. So let's find F31. F31 becomes what, yeah? K Q1 Q3 over R squared 3, 1 times unit vector of 3, 1. And that will give us what, yeah? F31 equals our K is 9 times 10 to the power of 9 times our charge 1 is 14 times 10 to the power of minus 6 times our charge 3 is 21 times 10 to the power of minus 6, all divided by distance between charge 1 and charge 3. Distance between charge 1 and charge 3 will be the sum of these two distances. Meaning from charge 1 to charge 3, we covered 0.12 plus 0.16. 0.12 plus 0.16 is 0.28, right? So 0.028 all what? All squared. From charge 1 to charge 3, the distance covered is 0.12 plus 0.16. Then we'll square it. Then times the unit vector from 1 to 3 is positive I. Is positive what? I, right? Is positive I. Now the next is to evaluate further. Let's evaluate 9 times 14, multiply with 21, right? With 21. This will give us F31 equals 2646 times 10 to the power of minus 3 I divided by 0.28 squared is about 0.0784. Okay, so let's go. Here we have, when we move our value here from the decimal point is here, right? I want to take off this minus 3 in the standard form. So I'll move my point 3 times. 1, 2, 3. Here becomes 2.646, right? 2.646. 2.646 divided by 0.0784. This is about F31 is about 33.75 I Newton. Okay, we have been able to find the force from charge 1 towards to charge 3. Our F31 is that. So let me evaluate again. 19 times 14 times 21. Okay, times 21. All right. Divided by 1000. 2.6 divided by bracket 0.28 all squared. Yeah, correct. Now let's find the next one is to find our F32, right? Our F32. F32 is can be expressed as what? as K, Q2, Q3 over R squared 2, 3 times unit vector of 2, 3. So that will give us what here? Our F 3, 2 becomes what? Our K is 9 times 10 to the power of 9, right? Times our chat 2, in this case, is minus 26 times 10 to the power of minus 6 times our charge 3 is 21 times 10 to the power of minus 6, all divided by the distance between charge 2 and charge 3. F32 means from charge 2 to charge 3. From charge 2 to charge 3, which is 0.16, 0.16, all what? All squared. So the next is to evaluate further. F32 becomes 9 times minus 26 times 21, 9 times minus 26, right, times 21 will give us about minus 4914, right? Okay, the unit vector here is plus I. Don't forget, because we are looking at from chart 2 to chart 3. From chart 2 to chart 3 is still plus I, all right? Okay, so minus 4914, okay, times 10 to the power of minus 3. I hope you guys know how we got this minus 3. 9 minus 6, right, is 3. So 3 minus 6 is what? Minus 3. Is that clear? Okay. So the next is divided by 0.16 all squared. That is about 0.0256. Okay, this value is in standard form. I can move my decimal point 3 times to knock off this, right? That will give us 1, 2, 3. So this is about 4 points minus 4.914 divided by 0.0256. All right. So this will give us about our F32. F32 becomes minus 191.9595. All right. 95. 199. 191.95. Okay. I Newton. Okay. So let me repeat that value again. 9 times 26 times 21. Okay, good. Divided by 1000. Okay. Then divided by again by 0.16 all squared. Okay, 191.95. Correct. All right. Then recall that we say that F3 is what? Our F3 is F32 plus F31 plus F32. It means I'm going to add our F31 plus F32 to find the force acting on chart 3, right? And F31, we got 33.75 I. F32, we got minus 191.95. So let's add up. So by the time we add up, our F3 becomes, let's go, our F31 becomes 33.75 I plus our F32, we have 191 minus 191.95 I, right? So our F3 becomes 33.75 I minus 191.95. 33.75. This will give us our F3 becomes minus 158.20 I Newton. 158.20 I Newton. Okay. Therefore, this is our answer in vector form. Therefore, our resultant force means what? F3 modules, right? Or F3 absolutes, which is equals to, like I said, here we have negative 158.20 I Newton. I will just do away with the negative. To find resultant means your answer should be positive. Resultant of a single vector like this means just take the absolute value of this. It means I will just take 158.20, 158.20 Newton. Then the direction becomes towards the negative, right? The negative x-axis, toward the negative x-axis. Why is it negative x-axis? If I'm to remove 158.20, what will remain here is minus I. My direction is towards the negative x-axis. Now let's see another example. Please, if you are following, indicate that you are following from the comments. Indicate that you are following from the comment section. Please indicate. Indicate. I want to see your. Please indicate. Please indicate in the comment section that you are following. Indicate in the comment section that you are following. Please indicate so we can proceed. And please, if you have not shared the link to others, please share. Let's share the link to others. All right, next question. Next question. Okay. We have another example. Excuse me, I'm coming. We are told that two charges, Q1 and Q2, two charges, Q1 and Q2, are located on the X plane at a position, are located on the X plane, on the SY plane rather, on the SY plane, at a position of arrow 1 R1 equals 3JM, R2 equals 4IM, and we are asked to find the force exerted on Q2. We have to find the force on Q2, given that Q1 is 500 microcoulomb, while Q2 is 100 microcoulomb. Let's solve this problem with this limited space here and see what we are going to generate at the end. Two charges, Q1 and Q2, are located on the XY plane. R1 equals to 3JM, R2 equals to 4IM. Find the force exerted on Q2. We are told that Q1 is 500 microcoulomb, Q2 is 100 microcoulomb. If you look at this system of charges are in the XY plane. And we are told that for Q1, the distance is what? 3J meter, meaning that charge 1 is along the y-axis because J represents the y component, right? While charge 2, the distance for charge 2 is what? R2, which is what? 4I. It means that charge 2 is located along the what? S-axis. Now, what do we do is that we're going to bring out our Cartesian diagram. Cartesian diagram, which is this. If you look at this here, the first charge is Q1, which is R1, right? R1 is 3J meter, meaning 3 meter in the y component. So what we do is that I'll bring out my charge 1. From this point here, this is my origin, right? From this point to this point here is 3 meter. Is that clear? Then we are told that charge 2 is located on the I component, which is the S component. Not just I, positive I. J, R1, charge 1 is positive J, plus 3J means positive. It means positive J. In the Cartesian diagram, this represents positive J. This is what? Positive what? I. So that means that charge 1 is located along the positive Y component, while charge 2 is located along what? The positive what? S component. Meaning from this origin, we have our charge 2 somewhere here. Okay, so distance from this origin to this point is what? Is 4 meter. Is 4 meter. Now the next thing is to draw a line here connecting charge 1 and charge 2. I will call it what? R. The distance between charge 1 and charge 2 is simply what? R. But we don't know the value of R. So what we do first is to find the distance between charge 1 and charge 2 using what we call the Pythagoras theorem. If you remember very well in my previous class, we talked about how to find the action of a force over another force along an inclined plane. That if I have a charge here, another charge here, the distance separating them is from here to here, which is this R. So what do we do to find the hypotenuse, the longest side, is by using the Pythagoras theorem, right? So from the Pythagoras theorem, using Pythagoras theorem, please, I hope you guys are seeing the board. The square of the hypotenuse, right? The rule says the square of the hypotenuse equals what? the sum of the square of the adjacent and what? And what? The opposite, right? It means that I'm going to square this, then equals to what? Square of 3 squared plus square of what? 4 squared. So r squared equals to what here? We have 4 squared plus what? 3 squared. And that will give us what here? R squared equals 4 squared is 16, 3 squared is 9. When you add up this, that will give us what here? 25. From here, it means that our r equals root 25. If we have r squared equals 25, to find out, I have to square root both sides, right? So our r equals to what here? 5 meters. So this distance is what? Somebody? 5 what? Meter. Now the next is to find the force exerted. Question said find the force exerted on chart 2. Find the force exerted on this chart 2. To find the force exerted on chart 2, it means that the direction of action is towards chart 2. Is that clear? It's simply towards what? Chart 2. If they say find the force exerted on chart 1, it means the direction of action is towards chart 1. Now, what do we do here? Is to find the direction of action. Since we are asked to find the force exerted on chart 2, this is my chart 2 here. So that means my direction of action will be towards this region, from this chart 1 downward, then this way. So my arrow is pointing this way. When the action gets to this point, it will continue this way, right? So from chart 1 to chart 2 means from this point to this point here, then from this point towards this point. But don't forget that if I have this simply means minus j, right? This means what? Plus j. Is that clear? This means plus I. This means what? Minus I. So look at this now. If we have a charge here, charge 1, and I have another charge here, charge 2. Is that clear? Our charge 2. And I'm to find the direction of action from charge 1 to charge 2. It means I'm going this way towards this side. This way means I'm going first towards the negative j, right? Then this way means I'm then going towards what? Positive I. So the direction of action first from charge 1 to charge 2 first is downward, negative j downward, then positive I this way. Negative j downward, positive I this way. If they say find the force exerted on charge 1, if it's on charge 1, it means I will move from here to here, right? Meaning what? Negative I, positive j. Negative I, positive j. But the question says find the force exerted on charge 2. That means from charge 1 to charge 2. So it means that my direction of action is from this charge 1 downward towards my charge 2. Now let's go. What then will be the Coulomb force? The Coulomb force will then be what? Our F2, right? We are looking for F2. The force exerted on chart 2 is same as F2, which is also same as what? F2, 1. In this case, we have only 2 charge. There's no need of doing superposition of forces here. Since I have just only 2 charge, it means that F2 equals to F21. What does F21 mean? From 1 to 2. So what we do here is to find this. Our F21 becomes what here? KQ1, Q2 over what? Over R squared, unit vector from 1 to 2 times, sorry, distance between charge 1 and 2 times unit vector of charge 1 and what? And 2. I repeat again, F2 is F21, which is KQ1, Q2 over R squared. Our R squared here means distance, square of the distance between charge 1 and charge 2, which is from here to here, right? And what do we got as the answer? We have 5 meters. So distance between charge 1 and charge 2 from the Pythagoras theorem rule, we solve as 5. Is that clear? So that means that here becomes our KQ1, Q2 over R squared times unit vector. Your direction of action is from 1 to 2. It's from 1 to 2. So that means the first thing we need to do first is to evaluate the direction of action. How do we find the direction of action for an inclined plane? It is not similar to that of horizontal. The previous example is not the same thing. It's not the same thing. This symbol here means unit vector. In physics, or in my yesterday's class, I explained this in detail. If you are just joining this live class, please ensure you go through the previous live class we had some days ago. Okay, we said that in physics, unit vector of a vector is equals to what? Vector r over what? R what? Modulus. If I have vector A to be Si plus Yj, to find the unit vector of this is simply what? Vector r over what? R modulus, which is equals to vector r is what? Is Si plus what? Yj, right? Over what's our R modulus? Square root of S squared plus what? Of plus Y squared. Is that clear? So what we do now is to find the vector for this force 1 to 2. When you get the vector force, then you can find the unit what? Vector. Now let's go. Let's watch. What then do we have here? Let's check this out. Unit vector for 1 to 2 becomes what? Let's check this out. From this diagram, for 1 to 2 means, first of all, we are going from 1 to 2. It means we are going negative j, right? Downward there is negative j. Downward. Here means what? Positive what? I. This way. Is that clear? So negative j times 3. When you move downward, we have negative j. That negative j times 3 will give us what? Minus 3j, right? We have minus 3j. Is that clear? Then when we move towards this direction, we have positive I. That positive I times 4 will give us what? Positive what? 4I. All divided by unit vector we said is vector R. This vector R here is what? Is minus 3j plus what? Plus 4I, right? Then we said over R modulus. What is the modulus of this vector? What would that be the modulus of this? Is simply what? Square root of what? Of 4 squared, right? Of 4 squared plus what? Minus 3 what? Minus 3 squared. Modulus simply means square of x plus square of what? Y. Our x here is what? Is 4. Our y here is what? Minus 3. That's what we just did here. So here becomes what? Unit vector from charge 1 to charge 2 becomes what? I can rearrange it because in vector, the first component that should come first is what? Is the I component, right? Vectors are always in this form. Si plus what? Yj. So it means I will bring this first. We have 4I minus 3j. Then divided by what? Square root of 4. Let's go again. 4 squared is 16. Minus 3 squared is 9. Minus 3 squared simply means minus 3 multiplied with minus 3. And that will give us plus 9. So that will give us what here? We have 4I plus, minus what? 3j, all divided by 16 plus 9 is 25. And the root of 25 will give us what here? 5. Now what we do next is to evaluate. Let's evaluate. I will divide this 4I with 5. Divide 4 divided by 5. That is about 0.8. So unit vector from 1 to 2 becomes this divided by this is 0.8I. 3 divided by 5 should be about 0.6. 3 divided by 5 is 0.6. So minus 0.6j. This is just our unit vector. I just defined the unit vector. Now let's see how we can solve for F21. Then what then is our F21? What then is our F21? Okay. What then is our F21? Let's go. Therefore, F2, 1 becomes, from our formula, we say KQ1, Q2. Our K remains 9 times 10 to the power of 9 times our Q1. Our Q1 is, again, that should be about 500. Q1 is 500. I've already cleaned that already. Don't forget that we say that Q1 is 500 microcoulomb. Q2 is 100, right? 100 microcoulomb. Q1 is 500, Q2 is 100. So that will give us what here? Times 100 times 10 to the power minus 6, right? Times, okay, our Q1, sorry, 500 rather, times our Q2 is 100 times 10 to the power minus 6, all divided by distance between charge 1 and charge 2. We have always seen the distance here is simply 5. So 5 what here? 5 squared. Don't forget we say times unit vector. What do we define our unit vector to be? This is our unit vector. And that will give us times what here? Times 0.8i minus 0.6j. Is that clear? Now let's finish up this. So we have 9 times 500 times 100. That will give us our f2, 1 becomes, our f2, 1 becomes, here we have 4500, meaning 450,000 times 10 to the power of minus 3 over 25, 5 squared 25, times 0.8i minus 0.6j. All right, so let's finish up. So at the end, we're going to have this. We have minus 3. Yeah, I can move my point 3 times to cancel out this, right? So we have 1, 2, 3. So here will give us 450 divided by 25. Here we have 18. So f2, 1 is 18 in brackets 0.8i minus 0.6 what? J. Okay. Then the next is to multiply this out. The next is to multiply this out. Okay, is to multiply this out. We have here 18 times 0.8. That will give us our f2, 1 equals 18 times 0.8 is about 14.4i. The same 18 times 0.6 is about minus 10.8 what j. Okay. Now in this case, don't forget that we have to find the force, right? The force exerted, the resultant force exerted on charge 2. The force exerted on charge 2. Now to find the force, exerted on Q2, we have to find the modulus of this force. In vector, if I have vector A to be xi plus yj, the modulus of A, vector A, becomes square root of what? Of x squared plus what here? Y squared, right? So the same thing here in this part here, if our A is this and if our force is this, it means our x is 14.4, while y is what? 10.8. Okay, the answer will end up to be 18 because from here, this is our modulus. But let me just prove this and see. So let's find our f21 modulus. That will give us square root of what? We have 14.4 all squared plus what? Minus 10.8 all squared. So 14.4 squared will give us root 207.36 plus 10.8 all squared will give us about 116.64. So what, by the time we add up these two, okay, let's take this will give us square root of 324. And the square root of 324 is simply what? Is simply 18 Newton. Therefore, our f2, 1 is equals to what? 18 what? Newton. Now, we have gotten the resultant force as 18 Newton. The next is to find the direction of action. The direction. Coulomb force is a vector force that has a size. The size of this force is 18. Now, the next is to find the direction of this force. Now, how do we find the direction of this force? Is by looking at this vector here. From this vector force, we can get our direction, right? From the vector force, we can get our direction. Okay, let's just solve this together. From the vector force here, we have F21 is 14I plus minus 10.8J. In the Cartesian diagram, look at this. This force here falls in what quadrant here? In this vector force here, X is positive. Don't forget that our vector is always SI plus what? YJ. So that means our X here is 14, which is positive. Our Y is what? Minus 10.8. So in the Cartesian diagram, where do you think this force will fall in? First, our S is positive. Our Y is what? Negative. That means this force will fall in the last quadrant, in the fourth quadrant. It will fall in here, right? It will fall in here. From the word cast, there's what we call cast in trig. Cast, C-A-S-T, right? Cast. A means all is positive. S means only sign is positive. T means only tangent is positive. C means only cosine is what? Positive. Is that clear? So the first thing we need to do is to find where this force is falling. And we have seen that it is falling in this quadrant, right? That shows that only cosine is positive. So the first thing we need to do is to find the reference angle, okay? Then when you get the reference angle of this force, we can then find the direction or the standard angle, which indicate the direction of the force. Okay, so let's check this out together. This will give us, since we agree that this force here falls in X is positive, Y is negative. So this force is located somewhere here. Now, there's what we call reference angle. We have learned this in first semester. Reference angle is always the angle between either the positive x-axis or the negative x-axis. For this case here, if I have these two here, these two angles, the reference angle will be here because this is positive x. If I have this line here, to be somewhere here, right? Good. The reference angle is always on the x-axis. But standard angle, which is the directional angle, is always measured from the positive x direction. So for this, since our vector falls in here, I will generate a right angle what here? Triangle. So let's work it out. Our s is 14 point what? Is 14.4. Is that clear? Our y is what? Minus 10 point what? 8. All right? Okay. The angle here is called our reference angle called alpha, right? Then our standard angle, which is the direction, is measured from the positive x-axis down to this point, which is our theta equals to 360 minus what? Alpha. To find this angle from this point to this point, angle at a point is 360. So that means from here to here is simply 360 minus what? Alpha. Is that clear? Okay, please go through my class. We did a class on this, on complex number, how to find reference angle and standard angle. I explained this in detail. But for this, to find the standard angle, because this force falls in here, I have to just put my reference angle here. When you generate this diagram, put it there, then get its standard angle, which is the angle from the positive x-axis down to this line of resultant, right? So let's see. Our resultant here is simply 18 Newton, which is what we have here, right? It's simply 18 Newton. Now the next is to find alpha. So using cos alpha. Why are we using cos alpha? Because this falls in the quadrant that says that only cosine is positive. Look at it here. I have cast from the word cast. The right quadrant for cosine is the fourth quadrant. The right quadrant for sine is the second. The right quadrant for tan is the third. Since this diagram falls in here, the right trig to use to solve for this alpha should be what? Cosine. And cos theta is from the word car, right? Car means what? Adjacent over what? Hypotenuse. So that means to find our cos alpha, it means I will use adjacent. This side here is called the opposite, right? Adjacent is 14.4. What's our hypotenuse? 18. So that will give us what here? 14.4 over what? 18. So let's go. So our cos alpha becomes 14.4 divided by 18. This will give us about 0.8. 0.8. So our alpha becomes cos inverse of 0.8, right? So we have shift cos inverse of this answer, which is about our alpha becomes 36.87 degree. Okay, but this is called the reference angle, right? This is called the reference angle, not the standard angle, not the directional angle. Therefore, to find the directional angle, we use our theta becomes what here? 360 minus 36.87 minus alpha. Do you get the concept here? So minus, okay, that'll give us our final answer becomes 323.13 degree. Final answer. This is our directional angle. That is our directional what? Angle. 323.113 degree. That is correct. Please, if you are following, indicate that you are following. If you are following, indicate that you are following. If you are getting it, indicate that you are following. All right. Please indicate. Okay, we are already moving forward. We are moving forward. Please indicate that you are following. Now let's see another example. This might be the last example, then we meet in our next class on electric field intensity. Okay, this question is not actually under action of force, but still under Coulomb's law. All right. The question says a force of 100 Newton acts between 2 point charges separated by a distance of 2 millimeters apart. Calculate the value of the force when the distance is increased to 3.6 millimeters in the same direction. Okay, I'm going to write the question here again. Then we'll solve together. All right, so the question here says a force of 100 Newton acts between 2 point charges separated by a distance of 2 millimeters. A force of 100 Newton is acting between 2 point charges, right? We don't know the size of the charges, so we're not told. But this force is acting between 2 point charges, meaning if I have charge 1 and I have a charge 2, the force acting is what? Is 100 Newton. The force of attraction or repulsion is actually 100 Newton, right? Okay, by distance, the distance separating the two charges we are told is 2 millimeters. 2 millimeters. The distance, our distance is 2 millimeter. All right, 2 millimeter is same as 2 times 10 to the power of minus 3. All right, minus 3 meter. Milli, I explained some things in our last class that 1 micro is same as what? 10 to the power of minus 6. 1 milli is same as what? 10 to the power of what? Minus 3. If I have 1 nano, which is smaller than n, is 10 to the power minus 9. If I have 1 pico is 10 to the power of minus 12. If I have 1 Armstrong is 8 to the power of 0, is 10 to the power of minus 10 meter. All of these are measurements, different measurements. But we are told that our radius, our distance of separation when this force is acting is 2 millimeter, which is 2 times 10 to the power of minus 3. Then the question says calculate the value of the force. So we have two forces here. So this is our F1. Let's call this F1, call this what? R1. For this distance, this is the force here. Then we have to find the force. The force when the distance is increased to 3.6. I'm looking for my F2 when the distance is increased to what? 3.6 millimeter, which is same as what? 3.6 times 10 to the power of minus 3 meter. Is that clear? Now listen, in our previous class, I gave two separate laws for Coulomb. If I give 3 laws, I gave the first, second, and the general law, right? In the first law, I say that between 2 point charges, so the force of attraction between 2 point charges is proportional to what? The product of their what? Charges, right? Is that clear? That same force of attraction is what? Inverse proportional to what? To the distance separating the two charges. The square of the distance separating the two charges. The first expression of Coulomb's law says the force of attraction, which is called the electrostatic force, right? Okay, between 2 point charges is proportional to the product of their charges, which is our F is proportional to what? Q1 times what? Q2. This is directly what? Proportional. It's a direct relationship, meaning that as the charges is increasing, the force is also what? Increase. The direct relationship. Then number 2 expression says that that same force is inversely proportional to the square of the distance separating them, meaning the more we separate the two charges, the 2 point charges, Q1 and what? Q2, the more we separate them, the lesser the what? The charge. The more the increase in distance leads to a decrease in force. Increase in the distance of separation will always lead to a decrease in force. That is why if you look at this, we are told that our distance is 2 millimeter, right? Where the force is 100. I mean, if we have distance of 2 millimeter, the force experience is 100 Newton. What do you think will happen if the distance is increased? The distance is increased, that means the force will also reduce. The force of attraction must reduce because increase in distance leads to decrease in the force. But let's see, if we then combine these two, that will give us the Coulomb general law, right? Which is Q1, Q2 over what? R squared. Then by the time we take off this sign, we have F equals to what? K Q1, Q2 over R squared times unit vector. Is that clear, somebody? Times unit vector. Then, looking at this first, second, and third expression, what do you think? Which of them do you think will be used to solve this problem? Will it be the first one, second, or third? Definitely, it won't be the first because the equation is not given us. We don't have any reference to any charge. We don't have any charge here. We only have force and distance. We are told that when the distance is 2, the force experience is this. When distance is now increased, what is the force experience? So that means the right expression to use is this second one. This second. Okay? We cannot either use what? Use this. Now let's look at the formula to use. Let's apply this formula and see what we're going to generate. Okay, from force is proportional to 1 over what? R squared. By the time we take off this proportionality side, that will give us what? Force equals to what? K over what? R squared. Is that clear? So can we cross multiply this? Cos K times 1 will give us K equals to what here? F R squared. This therefore means what? Our F1 R1 squared equals to what? F2 R2 squared equals to what? F3 or Fn Rn what squared. So I can use this relationship to find the force exerted when the distance is increased. Of course, we have F1 as 100. We have our R1 as 2 millimeter. Here we have our R2. We can find what? Our F2. Now let's apply and see what we're going to generate at the end of the day. So this will give us what here? What do we have here? Let's go. From here, our F1 R1 squared equals F2 R2 squared. For we to solve, we're going to use this to solve, right? So it means I will make my F2 to stand alone as the subject of the formula. We're going to make our F2 as subject of the formula. Make F2 as subject of the formula. That will give us what here? Our F2 becomes, okay, let me repeat this expression here. We have F1 R1 squared equals F2 R2 squared. So for us to make F2 stand alone as the subject, I will divide both sides by what? By R2 squared by what? R2 squared. So R2 squared can cancel R2 squared. We are left to what here? F2 equals to what? F1 R1 squared over R2 squared. So our F2 becomes, our F1 is given as 100 times our R1 is given as 2 millimeter, which is 2 times 10 to the power of minus 3, right? All what here? All squared. All divided by our R2. Our R2 is 3.6. 3.6 times 10 to the power of minus 3. All what here? Squared. So F2 becomes 100 times 2 squared is 4 times 10 to the power of minus 3 times 2 will give us minus 6. All divided by, I hope you know what happened here. I will square these 2, we have 4, then multiply the power here. Minus 3 times 2, we have minus 6. So what we have at the end of the day, 3.6 squared is 12.96. Here we have 12.96 times 10 to the power of minus 3 times 2 is minus 6. 10 to the power of minus 6, can we go with what? 10 to the power of minus 6. So we are left with 100 times 4 here. So F2 becomes 100 times 4 is 400 divided by about 12.96. Let's divide 400 by 12.96. That will give us about 30.86. We have 30.86. X6 was Newton. So when the distance is increased to 3.6, the force between the two charges becomes what? 30. It reduces to 30.86, which is also same as 30.9. 30.9. This is very simple. Okay, let's solve an equation. Please, if you are following, indicate that you are following. Okay, want to look at another example? Just give me some minutes. Let me get a question. Let's look at this question. This is under one of the properties of charge. Of charge. Properties of charge. So let's look at it together. Here we are told that a plastic rod is rubbed against a wool shirt. A plastic rod, a plastic rod, a plastic rod is rubbed against a wool shirt. Okay, acquiring a charge of minus 0.8 microcoulomb. Acquiring a charge of minus 0.8 microcoulomb. How many electrons are transferred from the wool shirt? How many electrons are transferred from the wool shirt? Okay. How many electrons are transferred from the wool shirt? Okay. We are told that a plastic rod is rubbed against a wool shirt, acquiring a charge of what? Minus 0.8 microcoulomb. Then we are told that how many electrons are what? Transferred, right? Now, we already know that recall that charge is equals to what? Ne, right? Charge is equals to what? Ne. Is that clear? Where N means number of what? Of electrons. N means what? Number of electrons. But the question says how many electrons are what? Are transferred. So what we do here is to make our N as a subject. N becomes what? The charge over what? The charge over electron. But don't forget that the charge here is minus 0.8 microcoulomb. And one electron is negatively charged. Please take note that electron is represented as minus 1.6 times 10 to the power of minus 19 coulomb. Please, it is minus 1.6. Electrons is one negatively charged. So the charge there is minus 1.6 times 10 to the power of minus 19 coulomb. So number becomes what here? Our charge becomes minus 0.8 microcoulomb means times 10 to the power of minus 6 divided by 1 electron means minus 1.6 times 10 to the power of what? Minus 19. Is that clear? Okay. So here becomes this sign, we cancel this sign. Our number becomes when you divide the whole of this, that will give us about, let me check the calculator, what we have there when we divide. 0.5 times 10 to the power of 13, 0.5 times 10 to the power of what? 13. So in a proper standard form, we're going to have 5 times 10 to the power of what? Power of 12. Power of what? 12 electrons. Power of 12 electrons. Power of 12 electrons. Please take note of this. Take note of this. Okay. I think we're going to stop here for now. We'll stop here for now. Then in our next class, when we meet, we shall look at electric field intensity, which talks about the strength of an electric what? Field. But let me drop an assignment for every one of us here. An assignment for every one of us. The assignment we have here says three charges. Three charges plus 20 Coulomb minus 30 Coulomb and minus 10 Coulomb minus 10 Coulomb are distributed as shown in the figure below. Are distributed as shown in the figure below. Okay, we have to find the resultant force acting on the resultant force acting on the number 1 20 Coulomb charge, number 2 minus 30 Coulomb charge. This is your assignment. Then the diagram is this as shown. This is the diagram here. We have the first charge here, the second charge here. Then we have a line here. Here we have 10 Coulomb. Here we have 20 Coulomb. Here we have, so minus 10 is here. Here we have 20 Coulomb. Here we have 30 Coulomb. The distance between this and this is 3 meters. Distance between this and this is 2 meters. And we have to find the resultant force acting on this charge. Let's say this is our charge 1, this is our charge 2, this is our charge 3, right? So this is how equation comes. So this is the equation here. This is your assignment. Please drop your answer in the comment section. Drop your answer in the comment section. All right, guys. So I think I'll be stopping this class now. We end our class now. Then we'll meet again in our next class on electric field intensity. On electric field what? Intensity. All right. We'll meet. Please make sure you do the assignment. Make sure you do the assignment. Very, very important. This is the assignment here. Very simple. All right, please, if you have any question, you can drop the question in the comment section. You can drop it in the comment section, please. Please, if you have any question, drop it in the comment section. Drop it in the comment section. I'm waiting. I'm online. If someone is asking, there is an error in the second example you gave in the solution. R is 5, not 25. Please check it well. The value of R is 5. Is 25 rather. When you find your R squared, 5 squared there is 25. Right? 5 squared there is 25. Check where. Check where. Go to the class again. Alright? Go to the class again. Okay, because I'm going through it again. Five squared there is 25. So what's the challenge? So please take note of that. Alright? Blessing. Have you seen your correction? Okay. So Ham from India, you are welcome. Thank you so much for joining us. Okay. Thank you so much for joining us from India. Shanshama, thank you so much for joining us from India. All right. Thank you so much. I have an exam on Electrostatics tomorrow. Love from India. Keep going, sir. I can't attend full lectures of yours, but love your dedication. Thank you. I really appreciate. I'm also grateful. I'm grateful. All right. So I'm ending my class today. tonight, rather. Then we're going to continue on Monday. Monday morning, we have our class at the center, right? On Chemistry 102, Organic Chemistry. Today in the morning, we learned the basic part of organic chemistry. We looked at the introduction aspects, how to classify organic compounds, the various terms we also considered. We define organic chemistry, and we just touched organic chemistry on the surface. So on Monday, I'll be going in detail. So please ensure you join us on Monday. Thank you so much. Thank you, guys. All right, guys. So I think I'm going to stop here. So see you guys in my next class.